So let's talk about what we're actually here to learn in this wonderful class. We did announcements. Great. Okay. Here we are. Okay. Data structures and algorithms. What the heck are they anyway? It's the name of the class. So I think I briefly said this as we were packing up on Monday, but computer science ultimately is just a bunch of switches on and off, right? That's literally every single computer is just a value of either on or off, which ultimately gets recombined and recombined and recombined into what we would call data. Data can be anything from numbers to what we would call strings, letters and characters, databases, media files, all of that good stuff. Stuff that we want to store and remember to take action upon later. So a data structure is how we take all of this information and organize it. You can almost kind of think of it as like the filing system or the organizational structure for data. And you probably have lots of data in your life that you organize in different ways according to how you use that data. You know, for example, maybe you have an email inbox and you have your email inbox by default set so that the most recent email always shows at the very top of your inbox. Maybe that's the thing you want to sort of address first. And then as a new piece of data, a new email comes in, it pushes the next most recent item down and then it shows up at the top. Does anybody happen to know the name of the data structure that organizes your emails in this way, just for funsies? This is dusting off some cobwebs from 143. I see some hands. I like it. Okay, here we go. What do you got? A stack. Yes, exactly. That's a really weird way to organize every single piece of data. But in the email situation, makes sense, right? Another type of data, maybe you have a whole collection of your notes that you take in class. And you take them one page of notes every single day. And then at a different point in time, you want to be able to go, hey, I need to find that set of notes for this specific day. So you want to go directly in and like maybe type in a keyword and find something associated with that keyword very quickly. That's a totally different way to organize your data, right? It's not really about the order. It's about how you find things within it. That might be using something we're going to talk a lot about called hashing, for example. Or maybe you have a series of bank transactions and you want to keep track of how many credits and debits you had, and it really matters the timeline of each of those debits and credits. You want to make sure that they're stored in the exact order they come in, and you might need to be able to sort of like access those at different moments in time. Maybe it's stored in something like a list. Those are all different ways of thinking about how you structure the data. While I was describing this, I said things like stack, I said things like list, I said things like hash. The annoying thing is those are all technically something we're going to learn more about in a little bit here called an ADT, but it's very easy to associate them with this idea of data structure. And I'm going to spend literally the next 10 weeks continually disambiguating these two ideas. But really, all of this is to get behind the idea that when we're trying to accomplish something with our computers are really good at storing data, and they're really good at telling or doing what we tell them. But it is entirely up to us to figure out how to organize things and what to tell the computers to do. The data structure is how we organize things. What we tell the computer to do is something we might refer to as an algorithm. An algorithm is really just a computer scientist obsession with essentially a list of instructions, an ordered list of instructions. A recipe to bake cookies is an algorithm. Dijkstra's Pathfinder is an algorithm we're going to talk a lot about. And so in this course, the reason it's called data structures and algorithms, and the reason that I was being really annoying on Monday, and I'm like, this is about creative writing, because now you should theoretically have all the syntax and all of the different structures and tools in order to write code. But we haven't talked about how to recombine this code in creative ways to address real world scenarios. And that's really what we're going to be getting into most of this course. And that's why this course is, used for interviews, because they're constantly going to be presenting you with real world scenarios. And the first thing you need to ask yourself is, what is the set of data that I need in order to accomplish whatever that goal is, and then what operations do I need to be able to do with that data. And then by picking the right data structure paired with the right algorithm, you optimize for whatever you think is the most important action that you're going to take in that design. A quick review. So I know this is something that you kind of do in 143, but I always have found that it isn't super clear necessarily by the time people get to 373. So there's sort of two different types of Java files. This is the basis of what we call object-oriented programming. So when you first started learning Java, you probably had a file that had a main method in it that had that header, public, static, void, string, bracket, args, all that goodness. And then every single method you had within that file had public, static, and then some return type. That file that had that main method in it was the executable file. That was the file that when you actually go hit the little red running man and JGrasp, or you hit the green place sign, I think, and other things, that's where the computer actually goes in and starts to run instructions from. But that program probably leveraged a lot of tools that were either created by the language or perhaps created by you. Those tools we sometimes call objects. It is still in Java in a .java file. It still has a public class name header around everything, but the difference with an object versus a client is an object is not an executable. It doesn't have a main method in it. Instead, it has instructions for how to construct a new instance of that object. That thing is called a constructor. If you can't tell, I'm just trying to dust off some vocab from 143 stuff. So if you remember the critters assignment from 14X, you had this sort of GUI UI thing here on the left. For those of you who didn't do this assignment, in the assignment we had this sort of animal kingdom, and this was the view of the animal kingdom. And then you had to write a bunch of objects. There were the individual animals, and they all had specific ways that they would roam about and attack each other and eat. Those were the objects. And it's going to be very important that you understand the distinction between these things, because you are going to be writing and designing a lot of objects. Those objects are likely going to be a lot of your data structures. And then you're going to have client code that fills up your data structures with whatever data it's collecting and maybe triggers any algorithms. But it is important for you to understand the distinction between these two types of things and how they ultimately partner together. If it helps, I kind of think of it as we're all, workers in a factory together. And maybe the client class, that's the factory foreman. That's the person that's okay, what comes next? What goes here? And then each object is a specialist. So every time we need to get something done, the factory foreman's okay, stack specialist. I need to give you some data and you need to order it in that special way that only you know how to do. Go off and do that and come back and report back to me. So the client class, that's what gets executed. The object classes, that's where all of our design and that sort of stuff happens. So I kind of mentioned this thing called an ADT. ADT stands for Abstract Data Type. You have probably heard of many ADTs already, and maybe you knew they were called ADTs or not. This is another delightful complication to this class, is now we're going to start to talk a lot more about the concept of abstraction, meaning how do I discuss things but separate the conceptual design from the technical implementation. What do I mean by that? For example, we could have an ADT like a list. Here we have a little sort of image representation of a list. And you may remember something called an array list from 14X. And I think there was even a more specific one called an array int list. Those are two different ways to implement the functionality of this more conceptual thing called a list. And these ADTs, these are really it's almost like a conceptual, shared theoretical API set across developers. We've all sort of decided as developers what this idea of a list is and how it's supposed to function. We actually have this for a number of different names, and we're going to learn about a bunch of different ones. But an ADT does not include any of the specifics of how you actually write the code. It just talks about what that final code should be able to do. So a list, for example, should be a ordered collection of things. Meaning, if I put something in first, I should know it's the first thing. If I put something in after that first thing, I should know it comes after that second thing. I also should be able to know exactly how many things are in my list at all times. I should be able to add things to my list at the front and at the back. So if I add something at the front, the thing that was previously at the front is now the second thing in the collection, and everything sort of shifts backwards. I should be able to insert things into the middle of the list, and everything sort of shifts backwards. Notice I have said nothing about code as I have been describing this. I've just been saying things and shifting and first versus second. And maybe your brain's already starting to think, well, like, okay, when she's saying first, maybe she means the index. No. I am trying to abstract away the idea of what functionality I'm trying to accomplish with the list compared to how I'm going to write code to actually make that happen. And in this class, the ADT is going to dictate the overall conceptual organization of the data. And each ADT usually has a set of operations that we know it must be able to accomplish. And then we're going to talk about the data structure, which is like the specific way we would write code in order to accomplish those things. And when we're trying to do a design for a specific scenario, we want to start with whatever the heck we're trying to do. We want to understand what data we're doing it on. We want to then pick the ADT, like, okay, like what sort of general things do I need to be able to accomplish by interacting with this set of information? And then we want to figure out which data structure we're going to pick to implement it to optimize for what we think is the most important thing. This is just a review of something called interfaces. I'm not going to talk about it, but I'm going to leave it in here. This is another review from 14X. This might start to look a little familiar here as well. So you might recognize these ADTs from the 14X program. Pen. Oh, and I made it so unhappy. Did you just crash? Fine, hang on. You might be like, hey, Casey, I noticed that you have all of your slides in Google Slides and that you post everything as a Google slide on the course website. And I would say, you're absolutely right. Why don't you teach from the Google Slides? And I would say, gosh darn, I do work at Google, but wow, they should really figure out how to let me mark up on a slide using my pen. And also those closed captions are really nice, right? Yeah. So that's why I promise that I think it is worth it for us to look at this in PowerPoint. Where are you going? Oh, I see. Hang on. An interesting window choice here, Windows 11. Okay, let's see. Where are we jumping in? Interfaces. Here's Java collections. Okay, let's see. Sending in good vibes. There we go. Okay, so here's some ADTs you may already be familiar with. We talked about list, and maybe this line of code looks a little familiar from 14X, where you would have these sort of more generic names on the left-hand side, and then the more specific names on the right-hand side. This is like the specific object type, meaning this was the bit of code that the computer was going to use in its ability to sort of execute against this, versus this was really sort of indicating what type of object that is. It does technically come from inheritance, which is why you sort of see this relationship here. And this is also just like annoyingly confusing within Java, which is also why I put this slide on here, because you notice, for example, this is just me reminding you of some specific Java syntax. Java happens to have its own stack implementation, and it is of type stack. Java does have a queue, but sometimes we use linked lists for it. Java has a map, and maybe you've seen a tree map implementation. I actually think this map thing is probably the best example of this, where map is another example of an ADT. Map being the ADT where you associate things as pairs of information, where one bit of the information is the key and the other bit of information is the value. A tree map is the specific implementation of that. And it is implemented with something called, in Java, an AVL tree under the hood, which we're going to learn a lot about. Here is the full definition. I think I mostly talked about these things. Here is the list of ADTs we're going to discuss this quarter. Like I said, you might find some things on here that are pretty familiar. I'll also say map is the thing we're going to probably be the most obsessed with, and you're going to see us probably call it a dictionary. Those are synonyms. I might go back and forth. You might hear me mostly call it a dictionary. It is totally okay if you use either. We'll know what you're talking about. You may have used a priority queue, but this is something we're going to end up implementing with a heap, which we're going to talk about that. And then we're going to spend the entire back part of the quarter working on this thing called graph. And if you're already ahead of me and you want to argue over whether or not graph is technically an ADT, I'd love to have that delightful religious debate with you at some point. But for right now, we're going to call it an ADT. Does anyone have any questions on this sort of like idea of data structure, ADT, and algorithm before we jump into a case study on the list ADT? Let's look at some examples then. I think it'll make things clearer. So I think I kind of gave you the basis of what the list does, but here's a little bit more detail. And so you have this concept of expected behavior from each ADT, and a lot of times that expected behavior is expressed in the format of these sort of function headers, these method headers like this. And so what it's saying is that I don't necessarily care exactly how you implement any of these methods, but in order for whatever object you are designing to achieve the check mark of being considered a list, it must have a function that lets you get out whatever is stored at a specific index. So you should be able to say, hey, I want the thing at the first index, which is technically the 0th index. Just to remind you, if it's been a minute since you've taken 1 for X, that we start counting from 0 in computer science. Or maybe I want the thing at the very end of the list, which would be at the list's size minus 1. So if I have 10 things in my list, the very last thing is at index 9. Maybe you want to set a value, meaning you want to go in and transform a value. Maybe it previously was one thing, you just want to change it to another. You want to insert and shift things down. You want to delete and shift things forward, all that good stuff. This is what we want to be able to do, and I'm going to talk about specifically 2 different data structure implementations, and then we're going to talk about which scenarios work best for each one. So the 2 different implementations we're going to talk about, and these implementations are what I would officially now call, these are data structures. Data structures. So the first one, chances are you're familiar, is something called an array list. This little angle bracket capital E that I have on here, that is Java's way of expressing generics. And so what the E does here is it's just a stand-in for whatever the type of thing is that's going to be stored in the array list. It technically is a stand-in usually for E element. So you might be accustomed to, say, making array lists of angle bracket integer, and that's an array list that holds all ints, or an array list of strings, or you could have an array list of array lists, for example, things like that. So you'll see that when we're thinking about how to create the array list, what we're going to use is we're going to use an array as the underlying data structure. There is a reason that computer scientists are obsessed with arrays. They are the underlying data structure literally in how your computer functions. So almost every single thing will have an array style implementation. And then in order to accomplish the array list with an array, remember that arrays in Java are what we call static sized. So when I go into Java and I say, give me an array of size 10, that array will be exactly size 10. It will never shrink in size. It will never grow in size. But the list ADT has to be able to do those things. The list ADT says a collection of elements that I can add to, I can remove from, I can move things around, right? And so an array doesn't by default have that behavior. So we're going to have to use arrays in a clever way in order to accomplish that. compare this to another style of list implementation, the linked list, which is also something hopefully we're familiar with from 143. The linked list will do exactly the same behavior, meaning it'll have exactly, and you can see here, right, from my little things, like there's a get in the array list version, there's a get in the linked list version, there's an append in the array list, there's an append in the linked list. But it's just a little bit different how we got about doing those things. And the underlying structure in the linked list category is this concept of individual objects we call nodes that point to one another, that are linked to one another. So if an array is sort of like one big contiguous block of memory, I like to maybe think of it as like a bookshelf, just that like one size. A linked list is like a bunch of different sort of like individual boxes that tell you how to get to the other box. So you can see here is like a basic visual of what the array list implementation of a list looks like. And you can see what we've got here is we've got a list and it's only referencing these first three items, meaning in my sort of visual representation of it, it would just be like these three items. But then we've got this thing called free space at the end. And that's because I do need to allow the list to grow. But like I said, the array, the actual thing inside of this concept of a list can't grow or shrink. So I always want to make an array that's a little bigger than I think I'm going to need it to be. And then I kind of fill it up. And then once I fill it all the way up, I got to make another array and like copy everything over and like make it bigger. And so in the array list implementation, I will always have this concept between what part of the array I'm currently using and what part of the array is available for use as my list grows. And so that's why we have these sort of distinctions between here's the list and here's the free space. The linked list, however, we get these sort of like perfect sized nodes to hold just a single element of the list. So if I only have 3 items in my linked list, I only have 3 nodes. If I want to add a 4th item to my linked list, that's totally fine. All I need to do is make another node, and then I change this reference if this is looking familiar to you, and I put like another item in here. And it's very easy for me to change the overall size of the linked list because I am not limited by this concept of this, like I have to make an array that can't grow or shrink. So these are the basics of how we would implement the list ADT with 2 separate types of data structures. Now let's talk about the trade-offs. So let's say we're implementing insert. If I call insert on this top one here, that is the array list implementation, you can see, again, I have that sort of distinction between like, this is the list, and this is free space. And since these are ints, I know I didn't put it, in here, but technically that would have a 0 in it by default. But I don't actually give any cares about what's stored in those spaces. I just think of that stuff as like, I'll get to it when I get to it, but that's just available for me at some point. But it's super then important for me to keep track of the size so I know which parts of the array are in use and which parts aren't. So now I've been asked to insert something in my list. I need to make space for it in the array. So what I'm going to do is I'm going to consume that empty spot in the free. I'm going to erase my line. And now I'm sort of using everything in the array. And the reason that I copied that 5 over is because whenever you want to move something in Java, if you don't want to lose it, you kind of need to make a new copy of it and then delete the old copy and then make a new copy of it and delete the old copy. And so there was space for the 5 to go at the very end. And I know I want to keep 5 at the very end because I'm inserting this 10 at index 0, meaning I want the 10 to go right here. So I'm going to make that 5. Now I have 2 5s, so I can replace the second 5 with a copy of that 4. Now I have 2 4s. I can replace that copy of the 4 with the 3. And now I have the original 3 values of the array list at their indices that they should be at after I accomplish the insert. And I've got 2 copies of 3. I don't need that. Now I can replace that 3 with a 10. And then I update my size. Now I have 4 items stored in my array list. So that is the specific code implementation of the data structure array list to accomplish the ADT function of list called insert. But I had to do all this like weird shifting. I had to copy all these things over, all that good stuff, right? That was sort of like the tax that I paid for using the array implementation. Versus, if I want to insert something in a linked list, I can just make a new node. And if you remember with linked lists, we have this kind of idea of something called a front pointer. And originally, that front pointer was pointing to this 3. But what I probably can do then is I can just make this extra 10. I'll have 10 point to front, so it'll just borrow that reference, and then I'll make front point to 10 instead. Meaning I didn't have to like touch 3, 4, or 5 at all, because they're not stuck in that specific spot in memory. They're just in their own boxes in memory, floating about, probably in our L1 cache somewhere, who knows. And I can just change these references. So right away you can see with linked lists, it's a little easier to move things around, but I do have to construct a whole new object every single time I need to add something to my linked list data structure implementation of the list ADT. So here, we've got 2 different data structures accomplishing the same ADT. Questions so far? Yes?
To insert into an array list, does the array need to be instantiated at that size, like the feature size?
So the question is, like, if I'm going to insert, does the array have to already be big enough to hold the thing? Is that what you're asking? So, great question. What's on my, and then we update size. On the next slide, I'm going to show you what happens when we try to do this type of insert, but we don't have enough space. Because I'll say from the user's perspective, me as a user, I only think about, like if I'm the client class, I don't know how the array list is implementing it. I don't know if the array inside is mostly full or totally empty or needs to grow. Like I can't worry about that. I'm just going to say insert 10. But we, as the designers of the array list object, we have to figure out the answer to exactly the question that you asked. When do I grow this thing? How big do I initially make it? How big do I grow it? And all of those things are designed as choices that you can make. I'm going to tell you what the conventions are for this particular implementation, but technically, you could totally decide. You could say grow it every single time if you wanted. You could start your array massive and never have to really grow it. But I'll talk about why you would choose any of those items, because you constantly have to be questioning the trade-offs. I'll just give you some more examples. So I click through this delete. So if I want to delete within the array list, I want to delete the thing at 0, so I want to delete that 10 that I just added. Again, I'm going to do this thing, kind of shifting thing where I don't need to remember the 10 anymore. I just want to get rid of it, right? I'm deleting that. So I'm going to consume that space. Why did you not do that? Okay, well, what theoretically happened there, you can see my animations are a little off, so I'm going to replace that 10 with a 3. And now there's 2 copies of 3. I'm going to replace this 3 with a 4. Sorry, I think maybe the animations got funky when I went between slides and PowerPoint because it's one of those days, y'all. And now I've got 2 copies of 5, but that's technically okay. Now I am at a point where my list looks like this, 3, 4, 5. I replace that 10 with a 3, and now all I need to do is just, there we go, change my size back down to 3. And so it's like I'm going to put that sort of like wall back here. And so now my list looks like 3, 4, 5, which is exactly what I wanted it to look like. I still had to do that kind of weird copying thing, but I don't care that this 5 is here. It could be any value, it doesn't matter. I'm just going to leave it there so I save myself an extra operation. As you can imagine, let's see how the animations go on the linked list. If I tried to delete the thing at index 0 here, I've got these sort of imaginary indices, but I technically don't have anything tracking them, so I kind of have to count in the linked list. That's one other thing that I kind of have to keep in mind. The array comes with these indices out of the box, but the linked list doesn't, so I have to, keep track of them myself with the nodes. But in order to delete something, again, I have that front pointer, and the front right now is just pointing at 10. If I just delete 10, essentially all I'm really going to do is I'm just going to skip the 10 node so that nothing's pointing to 10 anymore. And if you remember this idea called garbage collection, whenever you have a node in Java that nobody's pointing to anymore, it is considered unreachable memory. And this magical thing behind the scenes in Java called the garbage collector at some optimal point in time comes and just cleans up that memory. So I kind of think of it like you're holding a bunch of balloons, and then if you let go of the string of a balloon, like the balloon's still in the sky, but as far as you're concerned, that balloon's gone, right? And at some point, garbage collection comes and it sweeps all the balloons out of the sky. I hope that actually happens. I don't think it does. Please don't release balloons into the atmosphere. I think it's trash, but literal trash. So there we go. And then we just update the size. There we go. So that's how we do delete. Now, to the question about sizing. Append. So let's say I want to append, meaning add a new value into the array list implementation that should go at the end. So I want this list eventually to say 10, 3, 4, 5, 2, but I have no more space. Anyone want to guess what we need to do? Anyone have any guesses where we go from here? Can I grow the array? No? Let's see. Yeah, in the back. Yes, you have to create a new array. Exactly. I can't do anything. This array was made at size 4. It will always be size 4. And so the convention, to answer that question from before, is we traditionally start with a size of array that is what we would think a small or modest size considering the values that we're going to add. The conventional traditional value is 10. Is there a reason that it's 10? I don't know. It sounds good to us. That seems like a wieldy size of array. And then the convention is whenever we run out of space, we create a new array that is double the size of the current array. Now I said size of the current array, and what I should have said is capacity of the current array, because right now we have a size of 4, and this is a capacity of 4. Now we have a capacity of 8. So I can have space to add this to, and now all I got to do is just copy these items over. 10, 3, 4, 5, and then I can append that too. And so now I have a size of 5. Here's my line between the list and the unused space, though I still have a capacity of 8, so I can continue to grow this list. That doubling thing is just, again, convention. There are wonderful researchers that spend infinite amount of time trying to figure out the optimal sizing and when to resize and all that stuff, but this is usually the way that we've sort of landed to make this implementation easy. You'll find that over time, eventually you get to an array that's so large you don't really do a lot of this doubling anymore. But if we're now starting to think about the trade-offs between these two different implementations, as I get bigger and bigger into the arrays, that means I'm going to have larger and larger amounts of unused space, which might be exactly what I want. I want to be able to grow the array over time, but that means that I've just sectioned off parts of my computer to say preserve them for values that may or may not come. And so if I have something that's growing a lot very quickly in the beginning and then all of a sudden stops growing, I could end up with just like a bunch of unused space hanging around in my array list. Also, I had to like copy everything over, which means if I'm thinking about the runtime in terms of big O analysis, guess what? We're going to talk about big O almost every single day in this class. I know you probably have trauma around it. It's okay. We'll get through it together. But when we're talking about big O, we're usually talking about the runtime in terms of how many instructions we're running per number of items stored in our data structure. And anytime we have to grow the array, it means we have to go in and touch every single thing in the array list, right? It's like if you're moving from one bookshelf to the other, I got to pick up every book and move it over, and that gets really expensive. Versus if I want to append in my linked list, what do I need to do in the linked list situation? Anyone want to tell me? What's the linked list equivalent? Yeah. Make a new node. So my linked list always stays just perfect sized to how many items I need. And then I update that. So I'm going to talk a little bit about the trade-offs between these two things. And then when we come back on Wednesday, and we have a few minutes, please give me a couple minutes, I promise. Then we will talk about how we actually start to debate which design trade-off we want to accept for each scenario. So in the linked list, can anybody guess why in practice, not in Big O3, but in practice, a linked list almost always runs slower in just the act of looping over to print everything out in the list? If I were to just print out everything in the list, the array will always run faster than the linked list will, just to go from the beginning to the end. Any ideas why? Yeah.
Could be due to contiguous memory spaces allocation?
Yes, it could be due to memory space allocation. You're absolutely right. And that is because in the array situation, when I ask the computer, hey, give me a new array of size 10, what the computer really does is it goes into your computer's memory and says, give me 10 spaces all right next door to each other. Meaning if I'm looking at the thing at space 0, I know exactly where to look for the thing at size 1, at space 1, and the thing at space 2, and the space 3, and it goes really quickly through all of that stuff. We're also going to talk a little bit about how the computer moves that memory around between your RAM and your cache and your, like, all that stuff. And so the computer's really optimized for these ideas of contiguous blocks versus the linked list, though we draw them all nice here, like right next to each other, and it looks like these arrows are all nice and short. What that actually is every time you make a new node, it means go find exactly that space somewhere in memory. So if I have memory that's like a bunch of, a memory kind of looks like a bunch of matrices, this might be one node, this might be one node, there might be one node way the heck over here, and those arrows might be totally different sizes. And it might take me a lot longer to go find them in memory. So the array does take a little bit more space sometimes. I do have to do this copy thing, which is really annoying. I have to do the shifting thing. Remember all that? But it's like really quick and easy to find everything in that same bookshelf. The linked list, easy to move around. We're not using any unused space, but I'm like running all over the library trying to find where all these different books are. I'm going to leave you with those ponderances. Come back on Friday, and we're going to talk about some specific software scenarios that are optimized for each of those two different examples. Thanks so much, everybody. I'll stick around for a little bit and answer any questions if you have them.